welcome. Today I want to explore a simple but powerful idea within the persistence information weave, that temperature is not a force that creates structure, but a constraint that determines what structures are allowed to persist. From the earliest moments of the universe to stars, planets, chemistry, and life itself, temperature quietly governs which bonds can hold, which patterns can last, and which systems can evolve further. This discussion isn't about purpose or design, it's about permission, about how cooling, entropy, and gradients shape the space of what can exist long enough to matter. Section 1. Temperature, Entropy, and Thermal Permission Windows. When we describe objects as solid, stable, or persistent, we often forget how conditional those descriptions really are. At a microscopic level, matter is in constant motion, and that motion is set by temperature. Temperature is not just a measure of heat. It is a measure of how violently particles are being jostled by their environment. That agitation matters because every bond that holds matter together must continuously survive that motion. There is a simple physical constraint underlying this. Only bound states with binding energies significantly exceeding the local thermal energy scale, often summarized as kT, can persist. When thermal energy is high, weak bonds are broken as fast as they form. At extreme temperatures, even strong bindings cannot survive, and matter exists as plasma or free particles rather than stable structures. As temperature drops, agitation decreases, and deeper bindings are no longer overwhelmed by random motion. This creates what can be thought of as thermal permission windows. At any given temperature, only certain kinds of structures are allowed to exist for meaningful periods of time. Too hot, and atoms cannot hold electrons, molecules cannot form, and solids cannot exist. Too cold, and motion slows to the point that reactions cease, locking systems into static configurations. Structure lives in the middle ground, where motion exists but does not erase every attempt at organization. Entropy plays a central role here, but not in the way it is often caricatured. Entropy does not forbid structure, it constrains how structure must be paid for. At high temperatures, entropy production dominates and wipes out fragile order. At lower temperatures, entropy can be exported more slowly, allowing certain arrangements to persist. What survives is not what is favored by intention, but what is stable under the combined constraints of temperature, energy, and time. In this view, temperature does not decide what the universe wants to build. It decides what the universe can afford to keep. Persistence begins not with complexity, but with survival against thermal noise. Only once structures last long enough to matter can anything like evolution, chemistry, or life even enter the conversation. Section 2. Cooling as access, not causation. It is tempting to think of cooling as something that actively creates structure, but that intuition is misleading. Cooling does not introduce new forces, new rules, or new mechanisms into the universe. The laws governing particles, fields, and interactions are already present. What cooling does is far quieter and more profound. It changes which solutions of those laws are dynamically stable. In the earliest moments after the Big Bang, the universe was so hot that no composite structures could survive. Quarks did not bind into protons and neutrons, electrons could not remain attached to nuclei, and atoms, as we understand them, simply did not exist. This was not because the forces were absent, but because thermal agitation overwhelmed any attempt at binding. The universe was permitted to be simple, not because simplicity was preferred, but because complexity could not last. As expansion proceeded, the universe cooled and new forms of persistence became possible. Quarks became confined into hadrons. Protons and neutrons were able to bind into light nuclei during primordial nucleosynthesis. Much later, as temperatures fell further, electrons could remain bound to nuclei, allowing neutral atoms to form during recombination. With atoms stable, chemistry could begin. With chemistry, molecular bonds could persist. With still further cooling and suitable environments, solid-state structures could lock into place. Each of these transitions marks the opening of a new thermal permission window. Nothing fundamentally new was added to physics at these moments. Instead, the universe crossed thresholds where deeper bindings could finally survive the background noise. Cooling acted as a gatekeeper, revealing layers of structure that were always allowed in principle but inaccessible in practice. This perspective reframes cosmic history. Rather than a sequence of inventions, it is a sequence of access events. As temperature declined, the universe gained the ability to remember more, to store information in increasingly complex and durable forms. Atoms remember charge configurations, molecules remember bonding patterns, solids remember lattice structures. None of this required intention or design. It required time, expansion, and the slow removal of thermal agitation. Cooling, then, is not a creative force. It is the quiet condition that allows persistence to deepen. Once structures last long enough, they can participate in further processes, becoming substrates for the next layer of organization. What endures becomes the foundation for what follows. Section 3. Gradient engines and non-equilibrium structure. Cooling makes structure possible, but cooling alone does not build complexity. A universe that is uniformly cold is just as inert as one that is uniformly hot. In both cases, systems quickly reach equilibrium, and once equilibrium is reached, nothing interesting happens. There is no sustained motion, no directed process, and no mechanism for maintaining organized structure over time. What drives structure in the real universe is not temperature itself, but temperature differences. A gradient, whether thermal, chemical, radiative, or gravitational, creates direction. It provides a path along which energy can flow. That flow is what allows systems to maintain order locally while still obeying the second law of thermodynamics globally. A gradient functions as an engine. Energy moves from high potential to low potential, and in the process, some of that energy can be captured to build and maintain structure. Entropy is not defeated in this process. It is exported. Order persists only because disorder is produced elsewhere. This is not a loophole in thermodynamics, but its natural consequence when gradients are present. Stars are a clear example. Their interiors are extremely hot, yet structured behavior emerges because a strong gradient exists between the core and the surrounding space. Fusion, radiation, transport, and convection all ride that gradient. Planetary atmospheres exhibit similar behavior, with temperature differences driving winds, weather, and long-lived circulation patterns. Oceans maintain layered structures through thermal and chemical gradients. Even simple chemical reaction networks can sustain organization when supplied with a steady energy flow. Uniform systems equilibrate and forget. Gradient-driven systems remember. They maintain patterns, cycles, and structures precisely because they are never allowed to fully settle. Non-equilibrium is not a flaw of these systems. It is their defining feature. Seen this way, complexity is not something added to matter. It is something that emerges when persistence is coupled to flow. Cooling opens the door by allowing stable structures to exist, but gradients keep the door from closing by continuously feeding energy through those structures. Without gradients, there is no engine. Without an engine, persistence stalls. Section 4. Life as a thermodynamically consistent persistence loop. Life is often described as fragile or exceptional, But from a thermodynamic perspective, it is neither. Life does not violate physical law, nor does it require a unique temperature or a finely tuned environment. What it requires is far more specific and far more general: operation within a thermal permission window and access to persistent gradients that prevent equilibrium. At temperatures that are too high, complex molecules cannot remain intact. At temperatures that are too low, chemical reactions slow or halt altogether. Life exists in the middle region, where molecular bonds are stable yet dynamic, where reactions can proceed without erasing the structures they produce. This window does not define life by itself. It merely allows the chemistry life depends on to persist. What distinguishes living systems is how they exploit gradients. Metabolism is not a substance or a trait. It is a process that channels energy flow. Nutrient gradients, redox gradients, thermal gradients, and radiation gradients all serve as inputs. Living systems use these flows to continuously rebuild themselves, maintaining internal organization while exporting entropy to their surroundings. They persist not by resisting thermodynamics, but by cooperating with it. From this perspective, life is best understood as a persistence loop operating far from equilibrium. Structure is maintained because energy is constantly moving through the system. When that flow stops, persistence fails. Death is not the loss of matter, but the loss of gradient-driven renewal. Importantly, nothing about this requires purpose, intention, or design. Life does not arise because matter seeks complexity. It arises because, under certain thermal and energetic constraints, some chemical networks are able to maintain themselves longer than others. Once a system can persist by rebuilding its own structure, it becomes a platform for further variation and selection. Persistence precedes evolution. Evolution refines persistence. Life, then, is not an exception carved out from physical law. It is a natural extension of the same principles that govern stars, atmospheres, and chemical systems. Where thermal permission windows allow complex chemistry, and where gradients endure long enough, self-maintaining structures can appear. What lasts becomes what matters. One constraint across scales. When we step back and look across the entire arc we've just traced, a single pattern becomes clear. From the earliest moments of the universe to stars, planets, chemistry, and life, the same constraints are always at work. Temperature determines which structures are stable enough to persist. Gradients determine whether those structures can be sustained, transformed, and built upon. At the smallest scales, thermal energy decides whether particles can bind at all. As the universe cools, deeper and more complex bindings become viable, not because new physics appears, but because existing physics can finally express itself without being erased by noise. At larger scales, gravity organizes matter into long-lived gradient systems, creating stars and planets that maintain non-equilibrium conditions for billions of years. At still higher levels, chemistry and biology exploit those gradients to sustain intricate, self-repairing structures. Nothing in this chain requires intention, direction, or preference. What persists is simply what can survive under the constraints of temperature, energy flow, and time. Structures that last long enough become substrates for further structure. Persistence compounds, memory deepens, information accumulates not because it is favored, but because it is physically allowed to remain. Seen this way, the universe does not rush toward complexity, nor does it resist it. It permits complexity only when conditions allow, and it withdraws that permission when they do not. Heat erases, cooling stabilizes, gradients build, equilibrium forgets. This is the quiet logic beneath matter, stars, and life. not a force, not a goal, but a set of constraints that govern what can endure. And across every scale we can observe, the same rule holds. What lasts becomes the foundation for what comes next. What we've explored here is not a new force or a new principle, but a way of seeing familiar physics through the lens of persistence. Temperature sets the limits of what can hold together. Gradients supply the motion that keeps systems alive and evolving. Between those constraints, structure is allowed to appear, deepen, and sometimes endure long enough to matter. This way of thinking doesn't replace existing physics, it connects it. From the earliest bindings in a cooling universe to the fragile but resilient systems we call life, the same rules quietly apply. What persists becomes the groundwork for what follows, and what fails to persist leaves no trace behind. My name is Charles Carroll. Thank you for joining me in this discussion as part of the Persistence Information Weave. Join me next time. Who knows where science might take the conversation?